We often learn mathematics like an assembly line. You receive a set of inputs, follow a vertical list of instructions, and stamp out an answer. You don't ask why the rules work, you simply execute them. Take 45 times 28. The traditional method tells us to multiply 8 by 5, write down the 0, and carry the 4. Then comes a specific instruction. Before moving to the second line, you must drop a 0. If you ask a student why that 0 belongs there, they might tell you it's just a placeholder. But what is actually happening to the value of these numbers to produce the final answer of 1,260? This vertical process is optimized for speed. However, it functions as a highly abstracted formula, asking for rote memorization rather than a logical sequence. To see the math happening behind the rule, we have to look at the numbers in their expanded form. 45 is 40 and 5. 28 is 20 and 8. We can take those tens and ones and lay them over a geometric blueprint. 40 and 5 map across the top edge, and 20 and 8 map down the side. This grid, known as an area model, forces us to multiply every component of the first number by every component of the second. 40 times 20 is 800. 40 times 8 is 320. We repeat the process for the remaining values. 5 times 20 gives us 100, and 5 times 8 is 40. These four values are our partial products. When we add them all together, we arrive precisely at 1,260. Translating a multi-digit problem into physical geometry takes an abstract wall of numbers and turns it into manageable mental blocks. We can list these four results vertically to see how they interact with our original method. Let's place the standard algorithm side by side with our list of partial products. Look at the values in the first line. The 320 and the 40 from our grid combine to make 360. It is identical to the first row of the standard algorithm. As for that dropped 0, it appears because the 800 and the 100 combine to make 900. The 0 exists because we are actually multiplying by 20, not by a single digit 2. The standard algorithm functions as a highly compressed invisible shorthand for the physical geometry of the area model. This approach establishes the reason before the rule. It ensures students have a foundation in place value before they learn the shortcuts. These visual strategies act as a conceptual safety net. If a student forgets where to place a 0 in a compressed formula, their geometric intuition catches the error, keeping the equation structurally sound. This foundational understanding remains relevant as math gets more difficult. When students reach algebra, they will use this exact same geometric grid to multiply complex polynomials. Decomposing numbers into their place value parts makes the calculation predictable. It gives students a method to verify their work without needing to rely on a memorized set of steps. Knowing why a 0 is dropped or why a digit is carried ensures that the numbers on the page always represent a concrete, measurable amount.